The phrase supersonic seaplane sounds pretty unusual to today's aviation enthusiasts. The only thing that might sound more exotic is a flying submarine. Believe it or not, those kinds of crazy projects actually existed at one point. But a supersonic fighter that could take off right from the water was a very real aircraft. It was built by the American aerospace company Convair in the early 1950s. Today, decades later, many experts consider this entire concept to be an absolute dead end in aviation history. But back then, engineers and military planners saw things very differently. It is fascinating to look back and see exactly how the design and military thinking evolved during the creation of this unique aircraft. Every piece of military hardware is built to tackle a specific mission set. So what exactly was a water-based supersonic fighter supposed to do? World War II had just come to a close. This was a war where massive aircraft carriers really proved their dominance. However, these naval giants had two major drawbacks. First, their massive size made them incredibly expensive to build and maintain. Second, they were still pretty vulnerable targets in actual naval combat. These vulnerabilities became an even bigger concern at the dawn of the nuclear age, and it made sense. If an aircraft carrier took critical damage or went down, the Navy instantly lost its entire air wing. This meant the loss of dozens, sometimes up to 100 combat aircraft in a single blow. As the jet age arrived, aircraft got faster and heavier. This meant building even more massive carriers, pushing costs to astronomical levels. To break this vicious cycle, engineers came up with an idea that was brilliant in its simplicity. They decided to build a jet fighter seaplane. This kind of aircraft could easily be based on relatively small vessels. These included standard amphibious landing ships equipped with an internal well deck. The concept called for the aircraft to launch from the upper deck using a powerful catapult. Then, after successfully completing its combat mission, it would just land on the water and taxi right back into the ship's well deck. Even greater strategic advantages emerged when planning large-scale amphibious operations. As soon as the Marines secured an enemy beachhead, they could set up a staging area for these aircraft incredibly fast. They would use special portable ramps. This allowed the fighters to taxi straight out of the water and up onto the shore. All the equipment for this kind of forward operating base could be deployed by almost anything. It could be brought in by a heavy transport seaplane, a standard landing ship, or even a stealthy submarine. The logistics plan was pretty futuristic too. Aviation fuel was meant to be stored in special underwater tanks. These submerged tanks would connect via flexible hoses to refueling stations. These stations were mounted on securely anchored buoys just off the coast. Ordnance would also be kept in a hidden underwater cache. An initial stockpile of munitions would be kept ready to go on those same buoys. This meant the entire process of refueling and rearming the fighters could happen right out on the water. Military planners were convinced that this kind of waterborne airbase would be practically immune to enemy airstrikes. They called the setup a seadrome, plus the ability to disperse combat aircraft across different bays and inlets gave the Navy incredible operational flexibility. It also provided solid protection against a surprise first strike. In combat conditions, this concept meant you did not necessarily have to drag a giant aircraft carrier along. You could provide reliable air cover for an amphibious landing without one. However, flight operations were inevitably hampered by the strict limitations inherent to any seaplane. For instance, safe basing relied entirely on calm, storm-protected bays. Even moderate swells could make takeoff and landing impossible for a jet fighter. This unusual combat aircraft would have to spend most of its time sitting right in the water. It would be moored to a buoy. The plan was to haul it ashore only once a week. This was to thoroughly wash off the corrosive sea salt with fresh water. It was also to carry out maintenance and repairs. But no matter how hard the designers tried to make the seaplane fighter self-sufficient, it could never be completely independent. It always relied on traditional shore-based infrastructure. After all, you still needed reliable protected shelters for personnel. You also needed complex repair shops and storage for a ton of spare parts. Keeping the ordnance absolutely dry was a separate headache entirely. This was due to the constant humidity of a maritime environment. On top of that, for a water base like this to actually function, it required a dedicated auxiliary fleet. This fleet of launches and speedboats was needed to tow the aircraft. They also had to deliver fuel and supplies and ferry the crews. Military experts also had serious doubts about the overall combat survivability of the concept. The experience of past wars clearly showed a simple truth. Any target, whether a ship or an airplane, is far less vulnerable out in the open ocean. This is much less vulnerable than a stationary target moored off the coast, and the entire Seadrome concept permanently tethered these aircraft right to the coastline. When it came to flight performance, seaplanes always lagged behind traditional land-based aircraft. There's a whole list of perfectly logical reasons for that. First of all, seaplanes have to haul around specialized gear that standard aircraft just do not need. We are talking about heavy anchors, thick cables, and mooring and towing equipment. They also need powerful pumps to clear water out of the bilges and floats. On top of that, a seaplane demands heavy-duty waterproofing. Its airframe has to be significantly stronger than its land-based counterparts. This is because pounding through the waves during takeoff and landing puts far more stress on the structure. This stress is far greater than what aerodynamic loads ever produce. And of course, you cannot forget the floats. Even if it is a flying boat, it simply cannot do without outrigger floats for stabilization. All of this adds a massive amount of dead weight. It severely degrades the aerodynamic profile. This inevitably robs the aircraft of speed and maneuverability. To get a better picture of this, let us look at the Japanese Nakajima A6M2N seaplane fighter. Essentially, this was the legendary Mitsubishi A6M20 carrier fighter. It just had a massive centerline float bolted on. Both aircraft had the exact same 1,200 horsepower engines. But because of that added float, the seaplane ended up being roughly 68 miles per hour slower than its land-based counterpart. With flying boats, the situation was not much better. Just as a reminder, a flying boat is a specific type of seaplane. Instead of using massive floats, the fuselage itself is built like a ship hull. This provides the necessary buoyancy. For this kind of aircraft to get on step and break free from the water surface during takeoff, its underside features a stepped hull. These are sharp steps in the underside of the hull designed to break water suction. Because of these structural requirements, this kind of fuselage was inherently heavier than a standard one. Additionally, that sharp step bottom created massive aerodynamic drag in flight. A prime example is the land-based PB-4Y Liberator patrol bomber. It had almost the exact same range and could carry just as much payload as the famous British Short Sunderland flying boat. But the Liberator flew 30 to 40 miles an hour faster. This made it significantly more effective on combat missions. And this performance gap between land-based aircraft and seaplanes only kept growing throughout the 1930s and 40s. Toward the end of World War II, however, aviation saw three fundamental breakthroughs. Engineers realized that by combining these innovations, they could finally blur the line between land-based aircraft and seaplanes. These were the jet engine, radically new hull designs, and the hydro-ski. In the past, large piston engines and propellers had to be mounted as high above the waterline as possible. This was to keep the prop blades from striking the waves and kicking up corrosive saltwater spray during takeoff. Mounting them that high meant using heavy struts and pylons. This added a ton of extra drag and dead weight to the airframe. Naturally, jet engines do not like ingesting water either, but a jet intake has a much smaller footprint than the massive arc of a spinning prop. This makes it much easier to protect from sea spray. Plus, the engine could now be buried directly inside the fuselage. This allowed designers to ditch those heavy external mounts. They could shed excess weight and radically streamline the aircraft. As a bonus, the line of thrust now passed much closer to the center of gravity of the aircraft. This seriously improved handling. The new hull shapes came from months of intense research and wind tunnel testing. The main goal was to finally eliminate the traditional hydrodynamic step on the bottom of the hull. They also wanted to stretch out the fuselage and drastically reduce aerodynamic drag. With aircraft speeds pushing higher and higher, designers were banking on an interesting side effect. They figured that a rigid airframe, overbuilt to handle the severe aerodynamic stresses of high-speed jet flight, would inherently be tough enough to absorb the pounding of water landings. Ultimately, engineers hoped to design a flying boat hull that weighed virtually the same as a conventional land-based aircraft. The British were the first to put these two concepts together. They built a unique prototype for a jet-powered flying boat fighter called the Saunders Roe SRA-1. The aircraft had a fairly conventional layout for the early jet age. It featured straight to slightly swept wings. Its defining feature was the jet intake. which was cleverly integrated right into the nose. During flight testing, this seaplane fighter reached an impressive top speed of about 528 miles an hour. For the first time, a flying boat was posting numbers totally on par with the land-based jets of the era. Unfortunately, aviation tech was evolving at such a frantic pace that it quickly became obvious the Saunders Roe design had hit a dead end. There was no real room for further upgrades or speed increases. As a result, this incredibly ambitious program was eventually canceled. The third crucial piece of the puzzle was the aviation hydro ski. Standard snow skis are familiar to everyone, and water skis have been around for a long time too. But the bold idea of using a hydro ski specifically to help an aircraft get off the water came from engineers at the Stevens Institute of Technology and the National Advisory Committee for Aeronautics. This was known as NACA for short. It is worth noting that this was not the NASA space agency we know today. However, NASA would eventually be built on the foundation of this very committee a little later on. All this research was conducted with strict scientific rigor and on a massive scale. Various ski designs were rigorously tested in towing tanks. They were also towed behind high-speed research boats. Scale aircraft models fitted with these skis were put through their paces on special catapult rigs. Meanwhile, radio-controlled models were tested on open water and in actual flight. The results of these large-scale experiments proved the main point. Hydro skis could indeed lift a heavy aircraft completely out of the water. This eliminated the need for a step. The step is the sharp break in the lower hull that a traditional flying boat uses to plane during its takeoff run. Removing the step helped protect the fuselage from harsh wave impacts. Once the skis retracted into the hull, the aircraft had a perfectly clean aerodynamic profile. The decisive tests were carried out using a modified Grumman JRF-5 Goose. These tests definitively proved that hydro skis were practical. They provided excellent stability and handling during water takeoffs and landings. Convair was heavily involved in this development. While they did not build the turbojet engines themselves, they handled the development and integration of the entire power plant. In the late 1940s, Convair introduced a series of highly unconventional seaplane concepts. One of these featured what was known as a blended hull. The core idea was that the aircraft would sit deep in the water. The wings would actually rest on the surface to provide buoyancy. This allowed engineers to completely ditch bulky outrigger floats. Convair's approach was to first design an ideal hydrodynamic shape with perfect water handling. Then they would build a highly efficient aircraft around it. The engineers at NACA took the exact opposite approach. Their philosophy was different. First, design an aircraft with outstanding flight characteristics. Only then figure out how to make it take off from the water. The hydroski was the exact key needed to solve this complex engineering puzzle. Combining these two revolutionary concepts, the blended hull and the hydroski promised an incredibly efficient next-generation seaplane. Building on these impressive results, on October 1, 1948, the Navy's Bureau of Aeronautics officially announced a design competition. The goal was to create a brand new seaplane fighter. The requirements were demanding. The aircraft had to reach speeds of Mach 0.95. It also had to take off in 5-foot waves and be capable of flying night interception missions. By November 1949, the Navy had laid out strict operational requirements. They wanted a seaplane fighter capable of operating from forward bases in almost any weather condition. The key to making these highly ambitious plans a reality was the use of innovative hydroskis. Convair kicked off extensive development work on this ambitious new project. Engineers ran countless tests. They ran scale models in wind tunnels. They tested them at the David Taylor Model Basin and conducted high-speed research at the Aerophysics Laboratory. Designers decided to leverage their previous experience with the Delta Wing. This aerodynamic layout carried over from the development of the YF-102 interceptor. With this wing, the new aircraft was expected to hit speeds of Mach 1.5 at an altitude of around 30,000 feet. In the early stages of development, this unique jet-powered seaplane fighter was given the company designation Y-22. The aircraft was designed around a pair of Westinghouse J-46 turbojets. However, the design team had a contingency plan. If those engines were not ready in time for flight testing, they could temporarily swap them out for the more readily available J-34s. In August 1951, the project received its updated Navy designation XF2Y1. The X denoted its experimental status, and the F classified it as a fighter. By February 1952, the military ordered 12 production aircraft under the designation F2Y Sea Dart. Deliveries were scheduled to begin in 1954. As is typical with complex aerospace programs, timelines and order quantities constantly shifted. Ultimately, Convair built only 3 fully functional flying prototypes. They also built 2 static test articles for ground research. The Sea Dart first took to the water on December 14, 1952. This kicked off its hydrodynamic test phase at Convair's facility in San Diego Bay. The aircraft would carefully taxi out, progressively building up speed with each consecutive run. During one of these high-speed taxi tests on January 14, 1953, something unexpected happened. After skimming across the water for just over 1,000 feet, the seaplane accidentally broke the surface and became airborne. However, its official first flight would not be logged until later. The reason for the delay was a severe and potentially dangerous hydrodynamic issue that engineers dubbed ski pounding. Pilots reported that as soon as the aircraft pushed past 50 knots, the ride became incredibly violent. They described the sensation as feeling like the hydro skis were taking rapid machine gun fire from below, or like driving over a washboard at full speed. The vibration was so extreme that pilots physically could not read the cockpit instruments. During one test run, the violent shaking completely sheared off the nose-mounted pitot tube. This instantly knocked out their primary airspeed indicators. A detailed investigation isolated the root cause. It turned out that at high speeds, even tiny ripples in the water were striking the skis with tremendous force. Hitting actual wave crests made the impacts absolutely punishing. The hydrodynamic shocks created a complex feedback loop. This combined with the natural flex of the skis and the bouncing of the oleoshock absorbers. At its worst, the entire system, the water, skis, and struts, would enter a harsh resonance capable of tearing the airframe apart. To mitigate this destructive pounding, engineers had to redesign the ski geometry. They replaced the straight, trailing edges with tapered ones, modified the overall profile, and completely retuned the shock absorbers. This paid off, noticeably reducing the vibration. But no matter how hard the design team tried, they were never able to completely eliminate the issue before the program was ultimately canceled. The Sea Dart made its first official flight on April 9, 1953. By then, however, the ambitious program was already in jeopardy. The writing on the wall came from an unexpected source, Convair's own land-based interceptor, the YF-102. That jet shared the exact same delta wing design as the Sea Dart. Despite months of intense flight testing, it simply failed to break Mach 1. Naturally, it was a given that the Navy's XF2Y1 would suffer from the exact same transonic drag issues. Compounding the issue was the poor design of the air intakes and the aft section near the engine exhaust nozzles. On top of that, the J-46WE-2 turbojets they eventually installed on the aircraft simply failed to deliver the promised thrust. As a result, the expected top speed of Mach 1.5 fell to a disappointing Mach 0.99. This was well below what Navy brass demanded, having set the bar at a minimum of Mach 1.25. Naturally, this did not exactly inspire optimism among the admirals backing the project. To be fair, at the time, virtually no aircraft could push past Mach 0.9 in level flight, so Convair's engineers were truly pushing the envelope. Later on, the YF-102A interceptor finally managed to break the sound barrier after 4 months of testing. However, it took a major redesign using what is known as the area rule to make it happen. This success offered a ray of hope for the Sea Dart team. But Navy Command remained skeptical. They were looking at a seaplane that lacked top-end speed. And to make matters worse, it suffered from severe vibration and the violent pounding of waves against its hydroskis during the takeoff run. So what exactly is the area rule? Put simply, without getting bogged down in aerodynamics, the core idea is this. The cross-sectional area of the airplane needs to change smoothly from nose to tail. The most effective solution is to pinch the fuselage right where the wings attach. This creates a narrow waistline, often referred to in aviation as a Coke bottle shape. Thanks to this design breakthrough, aerodynamic drag at transonic and supersonic speeds is kept to an absolute minimum. A major blow came in late 1953. With the Korean War drawing to a close, the U.S. government initiated massive cuts to military spending. The Sea Dart project instantly found itself on the chopping block. Production orders were completely canceled. In the end, only 3 flyable airframes were ever built. This was along with 1 full-scale mock-up and an additional airframe specifically for static ground testing. Despite these setbacks, the Navy decided to keep the flight test program going. The experimental F2Y was fitted with upgraded J46WE-2B engines. These new engines featured afterburners for a significant boost in thrust. Because these new power plants were longer, designers had to extend the engine nacelles and reshape the aft fuselage. The primary goal of these new tests was to reduce the severe pounding on the hydroskis during takeoff. The first Sea Dart prototype kept flying in its original twin-ski configuration right up until the middle of 1954. The second XF2Y airframe joined the test program in early 1954. This aircraft featured extensive modifications, and some of them were pretty radical. Its fuselage was noticeably lengthened, and both the wing area and wingspan were increased. On top of that, the engine exhaust nozzles were blended much more smoothly into the aft section. Like the first aircraft, it utilized twin hydroskis, but this time engineers eliminated the beaching wheels. As a result, ground crews had to use a specialized transport dolly to move the second Sea Dart on land. Almost immediately after flight testing resumed, the team ran into a new danger. That danger was flutter. This severe aerodynamic vibration could literally tear the airplane apart in mid-air. Fortunately, they managed to fix the issue relatively quickly. And interestingly enough, this flaw only showed up on the second airframe. While the first prototype served mainly as a testbed to dial in the hydroski system, ship number 2 was used to push the speed envelope. It was the airframe used to test the upgraded flight control system and to evaluate the handling characteristics of the aircraft under various flight conditions. And then came a truly historic moment on August 3, 1954. Test pilot Charles Richburg put the aircraft into a shallow dive from an altitude of 33,800 feet. During this rapid descent, the fighter successfully broke Mach 1. With this achievement, the XF2Y Sea Dart made history as the first seaplane to ever break the sound barrier. And to this day, it is still the only one. Sometime in late 1954, riding high on the success of the area rule, Convair pitched an ambitious new proposal. They wanted to build a completely redesigned version of the aircraft. This was the F2Y Sea Dart. The designers planned to give it a single massive ski instead of 2. They also added an updated area-ruled fuselage to optimize aerodynamics. It would have one incredibly powerful turbojet engine. This would be either a Pratt & Whitney J75 or a Wright J67. On paper, the performance projections were staggering. The new F2Y was expected to hit a blistering Mach 2, but Navy leadership did not share that engineering optimism at all. The admirals stood their ground. They flat out refused to even entertain any new jet seaplane proposals. Convair had to completely fix the main problem first. This problem was the violent hydrodynamic pounding the skis endured during takeoff runs. Meanwhile, the second experimental Sea Dart prototype was still undergoing tests out in the open ocean. This was south of Point Loma. To keep these flights safe, an entire support fleet had to be deployed. Numerous high-speed boats and the large landing ship dock USS Catamount stood by at sea. At the same time, a rescue helicopter and a support aircraft kept a constant watch overhead. But the results were disappointing. Real-world testing showed that using hydroskis in the open ocean was incredibly inefficient. It was also downright dangerous, especially whenever even a minor swell rolled in. To fix this, in late 1954, the first Sea Dart prototype got a major overhaul. The twin ski setup was replaced with a single massive ski. This was mounted directly beneath the fuselage. It was centrally mounted on 4 special shock-absorbing struts. This single ski was so wide that engineers actually installed 2 small wheels at the rear of it. Paired with the tail wheel, this made towing the aircraft onto land a breeze. All told, the engineering team tested roughly 100 different ski variations. This was a relentless effort to find the perfect shape. But as is so often the case in aviation, solving one problem just created another. While the violent pounding against the hull during takeoff was greatly reduced, they could not eliminate it entirely. Instead, an even more serious threat emerged. The aircraft began to porpoise violently, and its directional stability was severely compromised. To tame this unruly fighter, the design team decided to upgrade the shock struts. They fitted them with an advanced variable stiffness system. Depending on the force of the water impact, the struts would automatically open a varying number of oil bypass valves. This helped absorb the shocks much more effectively. It was a highly complex piece of engineering, but surprisingly promising. Encouraged by these results, the team started gearing up for official evaluation trials for the Navy brass. But right before those crucial tests could even get off the ground, the program suffered a devastating blow. On November 4, 1954, the Navy and the manufacturer hosted a major demonstration. They showed off their new aircraft for the press and television crews. The stars of the show were supposed to be the XFY Pogo vertical takeoff fighter and the R3Y Tradewine transport seaplane. There was no intention of showing off the highly classified Sea Dart. However, the press persistently demanded a look at this cutting-edge jet seaplane. Keeping the project under wraps was pretty much impossible at that point. Rumors had been leaking to the media for a while. The aircraft was regularly flying right over San Diego Bay, in full view of a city with nearly 1 million people. The press held a lot of sway as the Fourth Estate. Antagonizing them was just asking for trouble. Eventually, Navy officials gave in and brought the Sea Dart out for the public. But a static display was not enough for the reporters. They demanded to see it fly. The leadership reluctantly agreed to a flight demonstration. Before takeoff, Convair test pilot Charles Richburg was given clear instructions. Take off, make a simple flyby past the grandstands at an altitude of 1,000 feet, and make a smooth water landing. Nothing more was expected of him. At first, everything went exactly to plan. But during the pass in front of the crowd at around 1,000 feet, the Sea Dart unexpectedly accelerated to nearly 570 miles per hour. Right in front of the crowd, the aircraft suddenly broke apart in midair. It plunged into the bay in a massive fireball. Rescue boats quickly pulled Richburg from the water. He was still breathing, but his injuries were fatal. The pilot died just minutes later. The Navy investigation board that reviewed this horrific crash came to a surprising conclusion. The tragedy had absolutely nothing to do with the Sea Dart's design as a seaplane. The real cause lay in the shortcomings of its early hydraulic flight control system. During the high-speed pass, the aircraft began to experience severe pitch oscillations. The hydraulic actuators simply could not handle the aerodynamic loads. The situation was critically worsened by pilot-induced oscillation. Richburg's involuntary, minute control stick movements to level the fighter only amplified the bouncing. It is worth noting that similar fatal control issues plagued many early jets of that era. So this was not a problem unique to the Sea Dart. Richburg was caught in a catastrophic loop. The airframe could not withstand the massive aerodynamic stress and literally disintegrated during the second violent nose-down pitch. This perfectly illustrates a fitting remark made around that same time by Soviet aircraft designer Andrei Tupolev. The best hydraulic actuator is the one that is not on the airplane at all. Following the tragic crash, the entire Sea Dart fleet was immediately grounded. Taxi testing on the water skis resumed almost as soon as the board published its preliminary findings. However, the F2Y never made another high-speed flight. Still, the project limped on. On March 4, 1955, the third and final flying prototype of the Sea Dart took to the skies. This specific airframe was equipped with twin skis. Their main engineering feature was a unique method of mounting small beaching wheels on the tapered trailing edges. These wheels could rotate, with their axis running parallel to the ski. Here's how it worked. After the aircraft taxied off the ramp and into the water, the wheels would rotate 90 degrees and retract. They sat completely flush inside the ski. Thanks to this design, the running surface of the skis remained entirely smooth. This was absolutely critical for hydroplaning across the water during takeoff. The primary mission of the third prototype was to test the twin ski configuration in the harsh conditions of the open ocean. However, the engineering team was not at all happy with the results. They wanted to shorten the takeoff run and reduce the time the airframe spent getting battered by rough seas. To do this, they decided to run an experiment. They attached solid propellant ray tow boosters to the aircraft. Each rocket produced about 970 pounds of thrust, with a burn time of 13 to 15 seconds. 2 of these units were mounted under each wing of the F2Y. The assisted takeoff was indeed a success. But that was the extent of it. The idea was ultimately dropped. Testing of the twin ski design was permanently halted on April 28th. The third Sea Dart prototype never flew again. Meanwhile, the first Sea Dart prototype, equipped with a monoski configuration, continued its flight testing. But the team soon ran into a new, unexpected problem. Sea salt began accumulating rapidly across the airframe. These deposits posed the greatest threat to the engine compressor blades. Interestingly, the salt was not even coming from direct sea spray. It was simply settling out of the damp, salty ocean air. When the engines were running, these hard crystals could break loose. They could get sucked into the intakes at high speed and literally shred the compressor blades. Their solution was surprisingly simple. Just wash the salt away. To do this, they installed a 20-gallon onboard freshwater tank. Right before the takeoff roll, while the engines were still idling, water was sprayed directly into the compressor intakes. This effectively flushed out the salt buildup. This system turned out to be incredibly effective. Around the same time, another series of tests was underway. The goal was to determine the maximum allowable sink rate during a water landing. They managed to push this figure to almost 19 feet per second. The airframe absorbed the impact loads perfectly. After the tragic death of test pilot Charles Richbourg, confidence in the Sea Dart program took a massive hit. But despite the setbacks, the Navy decided to push ahead with final evaluation flights in May 1955. Those flights clearly demonstrated that the single wide ski configuration handled wave impacts much better than any twin ski design. But there was a major trade-off. The monoski introduced severe directional and lateral stability issues. The aircraft struggled to hold a heading and oscillated constantly on the water. The review board came to a disappointing conclusion. Ironing out all these design flaws and bringing the jet up to an acceptable safety standard would take at least another year of engineering work. That kind of timeline simply did not work for the Navy. Their interest in this exotic jet-powered seaplane fighter faded fast. Even so, the sea trials continued for a while purely on institutional momentum. So what did a typical test profile for this unusual aircraft actually look like? The standard procedure went something like this. The pilots would spool up the engines while still on dry land. From there, the aircraft used its own small beaching wheels. These wheels were integrated directly into the skis and the lower tail section. They allowed the jet to taxi down a concrete ramp and slip into the water. These wheels had their own independent brakes, but instead of steering with standard rudder pedals, the pilot controlled them from the cockpit. This was done using 2 dedicated levers on the right-hand console. The test pilots absolutely hated this setup, though to be fair, they never actually lost control of the jet. Pulling back on both levers applied the brakes evenly. Pulling just one would steer the aircraft in that direction via differential braking. During this ground maneuvering, the skis were lowered into their initial position. In this configuration, they sat perfectly flush with the hull. This allowed the jet to transition safely from the ramp into the water. As soon as the aircraft entered the water, the small wheels on its skis pivoted 90 degrees. This allowed them to stow completely flat and flush with the skis. This eliminated any hydrodynamic drag. Taxiing this fighter on the water was surprisingly easy. It used a combined water rudder and hydro brake system located at the tail. If the pilot needed to make a sharp turn, all they had to do was use asymmetric engine thrust. But there was a catch. Testing showed that if only one engine was running, the Sea Dart would become hard to handle. It would also struggle to maintain a steady heading. Under normal conditions, with the engines at idle, the aircraft cruised along at about 2 to 3 knots. If the pilot deployed the tail brake and fully extended the skis, the speed dropped even further. It went down to just 1 to 2 knots. As they lined up for takeoff, the pilot had to do some precise maneuvering. They had to find the perfect balance to compensate for both wind direction and ocean currents. Right before starting the takeoff roll, the skis were fully extended with the push of a single button on the left console. The takeoff roll itself ran almost parallel to the swells. However, they tried to keep the nose pointed into the wind as much as possible. Interestingly, during testing, the Sea Dart successfully got airborne even in strong crosswinds. It handled angles up to 60 degrees off the takeoff heading. Once the pilot advanced the throttles, the aircraft began to accelerate. Passing the 8 to 10 knot mark, the hull lifted out of the water. The airplane then rose onto its skis. To reduce pilot workload during such a complex maneuver, engineers designed an automatic control system. This system managed the skis during the takeoff roll. As soon as the hull cleared the water, the system temporarily locked out maximum afterburner. The skis then automatically shifted into a specialized shallow planing position. Because they were not digging into the water as much, hydrodynamic drag dropped sharply. As a result, the aircraft started picking up speed much faster. At this point, the afterburner lockout was disengaged. By the time the speed hit 50 knots, the skis fully extended again. This clever sequence allowed the airplane to plane smoothly and confidently across the surface. It significantly reduced the harsh wave pounding on the airframe. As the speed climbed to 100 knots, the pitch angle of the aircraft sat between 2 and 5 degrees. Once it accelerated to 125 knots, the angle reached the ideal sweet spot for takeoff. This was between 17 and 19 degrees. After this, the fighter finally lifted off. Of course, it was not the most comfortable ride. During the acceleration from 50 to 125 knots, the aircraft experienced severe vibrations. This happened even in waves just 2 feet high. The waves slammed hard against the skis. This subjected the airframe to up to 5.5 Gs at a frequency of 15 to 17 Hz. It took a serious physical toll on the pilot. Once in the air, the aircraft flew completely predictably and remained perfectly stable. There were no nasty surprises, though it is worth noting that the early hydraulic flight control systems were still pretty raw. They definitely needed more refinement. Visibility from the cockpit was perfectly adequate. The cockpit featured a unique wedge-shaped canopy. Convair planned to improve this visibility even further for production models. However, another issue cropped up. At certain sun angles, the instrument panel would fall into deep shadow. This made it tough for the pilot to read critical instruments in flight. On top of that, the fighter was just plain underpowered. Even with the J-46WE-2B jet engines, thrust was still lacking. This was true even though they featured afterburners. As a result, acceleration and climb rate were far below what a combat aircraft needed. Plus, another major issue surfaced. Those J-46 engines were highly vulnerable to salt buildup inside the compressor. Let us face it, that is really not the kind of trait you want to see in a seaplane. On the flip side, the engineers did a decent job protecting the intakes from salt spray. With proper maintenance and regular freshwater washdowns, the engines could reach their design life without major failures. The landing sequence for this seaplane fighter was essentially the takeoff process in reverse. The pilot fully extended the hydro skis and flew the aircraft smoothly down to the water. Touchdown occurred at a pretty high speed. This was about 120 knots. After that, the airplane skimmed across the surface. It bled off speed rapidly as the hull settled into the water. When the speed dropped below 6 knots, the skis automatically shifted into taxi mode. Then the small beaching wheels pivoted into position. Thanks to these wheels, the aircraft could taxi right out of the water. It could drive up a concrete ramp under its own power, just like a true amphibian. The experimental Sea Dart made its final flight on January 16, 1956. The main goal of the test was to push the aircraft's open ocean capabilities to the absolute limit. The conditions were brutal. They faced sea state 5 with swells up to 10 feet. A stiff wind was blowing at over 20 knots. This wind was about 45 degrees off the swell direction. Test pilot Billy Long was at the controls. During the takeoff run, the pounding and severe vibration was intense. The waves were slamming against the hydro skis so badly that he tried to get airborne as quickly as possible. He pulled back on the stick way too early. The fighter pitched sharply into the air. However, it lacked the airspeed to sustain flight and slammed violently back down. The aircraft then began to porpoise violently across the waves. For seaplane pilots, a severe porpoise is an incredibly dangerous situation. The impact loads on the airframe were brutal. They spiked the G-forces in the cockpit to a punishing 8.5 Gs. In those frantic seconds, Long's only thought was to keep the nose from digging in. He needed to get the jet in the air at all costs. Eventually, the Sea Dart muscled its way off the turbulent water. After climbing out and flying a wide pattern over the bay, Long came back around to land. But the touchdown was far from smooth. It was marked by another series of brutal slams against the swells. During one of the bounces, he hit his head hard against the canopy, bloodying his nose. Despite the injury and violent pounding, Long showed incredible airmanship. He kept the aircraft from submarining, he brought it to a quick stop, and taxied safely back to base in San Diego. This would be the final flight in the history of the Sea Dart. The final nail in the coffin for the ambitious program was the arrival of the Forrestal-class supercarriers. They earned that classification due to their massive displacement for the era. It ranged from 66,000 to 82,000 tons. Ultimately, the exotic seaplane concept simply lost out to the brand new heavy carriers. These were the ships it had originally been meant to supplement. In January 1956, the U.S. Navy dropped its requirement for a jet-powered seaplane fighter. After that, the project was shut down for good. Wrapping up the story, it's worth noting that engineers knew exactly how to fix the Sea Dart's design flaws. With the right amount of backing and funding, this jet really could have been developed into a fully operational supersonic fighter. Under those conditions, it's highly likely it would have been adopted by the U.S. Navy. On top of that, the aircraft had every chance of setting a string of world speed records for seaplanes. Even so, its service life likely wouldn't have been very long. This is because the basic airframe simply had no room left for future upgrades. What about the Soviet Union, America's main Cold War rival? Interestingly enough, Soviet designers never even considered a concept for a similar aircraft, and there's a perfectly logical explanation for that. It's incredibly hard to imagine any practical use for a seaplane fighter operating on open water in the harsh Soviet climate. This is especially true during the fall and winter months. An aircraft like that would quickly ice over, completely losing its combat effectiveness. If nothing else, the Soviet Union saved a massive amount of R&D money by skipping the idea entirely. Clearly, the Sea Dart was designed with an eye toward future conflicts in tropical or warm water environments. And as we know, the Soviets didn't exactly harbor grand plans to invade distant tropical islands. Overall, the development history of this unusual seaplane proves the old adage once again: the military is always preparing to fight the last war. This jet would have been the absolute perfect weapon for the Pacific Theater during World War II. But it turned out to be completely unsuited for emerging Cold War threats. Despite the program's cancellation, a minor miracle happened. Every single Sea Dart that survived the grueling flight test program has made it to the present day, and they are now proudly on display in aviation museums. It is a prime example of how carefully America preserves its aviation heritage and unique technological artifacts, ensuring future generations can see the bold engineering dreams of the past firsthand.